Human vision and the cameras we build can only see what lies in direct line of sight. This is X-band radar non-line of sight imaging. Picture a car approaching a blind corner. The hazard is hidden, completely out of sight. Non-line of sight imaging reconstructs that hidden geometry from signals that bounce off a relay surface, like a wall. But each diffuse bounce scatters energy in every direction, and the return falls off quadratically with distance. Eye-safe optical and infrared systems are power-limited, so they reach only a few meters, far too short for driving. The key is wavelength. At optical or 77 GHz bands, it is smaller than the wall's surface roughness, so signals scatter diffusely. We use X-band radar at 10 GHz, a 3 cm wavelength, far longer than the roughness of a typical wall. Now the wall acts like a mirror. Reflections become specular, the hidden scene is strongly illuminated, and the range grows dramatically. Prior non-line of sight work spans 3 regimes. Optical methods reach centimeter-level accuracy, but only over a few meters and mostly indoors. Millimeter wave radar at 77 GHz adds range, yet still suffers from diffuse and multipath reflections. Ultra-wideband radar penetrates well, but its angular resolution is very coarse. Plotting these on a map of range versus angular resolution makes the gap clear. Our X-band radar, a 3 cm wavelength at 10 GHz, reaches 40 meters with high angular resolution, roughly 10 times the range of optical NLOS, while staying robust to ambient light with strong penetration. We propose an X-band radar NLOS image formation model. A radar wavefront reflects off the relay wall, enters the hidden region, scatters from the object, and returns after a second reflection. In general, this is a triple integral over beam patterns, reflectances, attenuation, and path length. But at X-band, the 3 cm wavelength far exceeds the wall roughness, so reflections are specular dominant. The integral collapses to a single mirror path. The wall acts as a mirror, placing the hidden object in a virtual scene behind it. We further steer the array into a range, azimuth map. X-band's long wavelength, though, leaves it blurry and low resolution. Our dense prediction module processes the complex-valued array map with a SwinUnet transformer, producing a dense confidence map that localizes and classifies every peak, upsampling the angular resolution and separating hidden echoes from direct ones. Zoomed onto the scene, the blue points are line-of-sight returns, direct objects like the wall, while the yellow points are the mirrored non-line-of-sight responses. The geometry-aware module turns those detections into real positions. A global geometric step reflects each mirrored point across the relay wall, while a local MLP with attention predicts a residual correction. Combined, the analytic reflection plus the learned residual give the hidden point's true position. Mapped back onto the scene, the brown points are line-of-sight detections on the wall, and the pink points are the reconstructed hidden targets. We built a custom X-band radar prototype. It's an FPGA-based RF system with a 4x8 antenna array, an up or down converter, and electronic beam steering. A co-mounted LiDAR and camera provide ground truth, captured simultaneously across outdoor scenes. To generate training data, we built an end-to-end radar simulator. It synthesizes the antenna radiation pattern and renders realistic driving scenarios, then models wave propagation with FDTD and multipath ray tracing. This produces realistic range, azimuth maps whose statistics closely match real captures. We test on real driving scenes, parking lots, city blocks, garages, and driveways, recovering hidden vehicles the ego camera cannot see. In the zoomed-in recovery region, the pink predictions land right on the orange ground truth vehicle. At ranges up to 40 meters, an 80-meter round-trip path, and even at night, when camera perception fails. Across both simulated and real data, the method delivers accurate dense prediction and reconstruction. Our geometry-aware reconstruction improves F1 by 56% and reduces chamfer distance by 65% over the best baseline. X-band radar makes large-scale, around-the-corner perception practical for the real world. Thanks for watching. Visit our project page for more details.